Okay, welcome to the second class meeting of the EC 202, Introduction to Probability and Random Processes. Today, I planned to cover initially up to section 1.4, but just before I come to here, I changed my mind. But usually, I fail to achieve my goal for the coverage. So I'll do my best to cover all these subsections related to chapter 1. So chapter 1 is about probability. You learned the notions of random variables in your high school probability course. That is not appearing yet. So we are going to basically talk about probability of events and Bayes rules, or something like that, which you are very familiar with. However, I will try to be as rigorous as possible. So you will see something's not comfortable compared to what you already know about this chapter. And as I told you last time, many of you already have taken our post-tech math department's probability and statistics. And in that course, you also learned a lot, but probably you already forgot most of the things and still have almost the same knowledge as you were at the second or third grade high school student. So I will talk a little bit more about what you learned about the probability theory. So let's start from one interesting problem written in Korean. So let me read it for you. So there were Socrates and Plato. They were kind of teacher and student. And this is very, very famous in Western culture. Probably you know that Plato's book is almost forgotten in the Western hemisphere, but kept in the Islamic civilization. And in the Middle Age, it is kind of imported back to the Western. And from that time, through the Renaissance and afterwards, the Western people examined every sentence, every paragraph, every chapter of Plato's book. And there were very interesting stories like this. So have you read it? And you get the problem? So this problem looks like nothing to do with probability problem. But interestingly, this kind of philosophical question or conversation between Socrates and Plato kind of inspired many mathematicians afterwards. So if you click the link I provided here by the Wikipedia, you will find some mathematicians who formalize this problem into a probability problem. And I'm not going to spend time to derive the solution to the probability version of this one. And what I want to just say is that probability theory a lot helps to clearly think some even philosophical questions. And if you are interested in the just the answer, let me tell you. So this problem is formulated as a probability problem named secretary problem or marriage problem, as the episode says. Or sometimes it's called best price problem, where you have n interviews, for example. And after each interview, you have to decide whether to hire the secretary or just see the next candidate. You cannot turn back. And the key is that you know how many candidates, the maximum candidates you can interview, but you don't know what kind of variation, maximum, minimum, no information at all, but you have to choose. And you want to choose best candidate as your secretary in the secretary problem. interesting story, and the solution says the number E appears here. So asymptotically, so for N sufficiently large, your best strategy, which maximizes your selection of the best secretary candidate, is like this. You interview around 1 over E candidates. Just record the score and pass. And then after finishing the interview of 1 over E, then probably you have the maximum number. And from now on, what you do is that if a candidate shows score greater than that number, the maximum number, you hire the candidate. And you know this number E is approximately, I memorized it. It's very easy to memorize, right? And then it's around 30-something%. I forgot it, okay? And this strategy is the known to be best strategy. And what would be the probability of hiring the best candidate? That is also 1 over E. So it's very interesting, right? The number E, the Napier number or Euler's number, does not only appear in compound some interest rate computation. It also appears in very, very classical philosophical question between Socrates and Plato. But unfortunately, we are not just studying the probability. We are studying probability and random processes for electrical engineers. And our goal is not to solve that problem, but to have the knowledge, principal probability modeling capability of signals and systems with uncertainty in electrical systems. So as you see that, signals and systems course, by the way, how many of you have taken it already, signals and systems? Okay, so around half. In the course of signals and systems, there was no uncertainty at all. But in reality, we confront a lot of cases with signals and systems with uncertainty. And probably at this moment, your only choice is to rely on some strict inequalities, greater than or equal to. So you have tolerance and want to design and analyze signals and systems. But as I just have shown you in the first class meeting, there are other cases where you need probabilistic modeling. So I want to kind of give you some ideas how to handle that kind of cases where signal with uncertainty and system with uncertainty appears. Got it? So, by the way, probability theory is actually a subject of measure theory, in Korean 측도론. And measure theory is a kind of advanced course of mathematical analysis, in Korean 해석학. So if you are a math department student, probably you are or you have already taken introductory real analysis, and probably you are going to take measure theory. Then I recommend you to take measure theoretic probability course. That will kind of give you much more rigorous foundation on probability theory. And you will also find that I lied a lot in this course. And most of the lies were white lies. Because if I talk too much about measure theoretic probability, then you will all drop before next week. Got it? So I will try to minimize this measure theoretic aspect as far as possible. Got it? Anyway, so these are all terminologies you are going to study and learn. So you read it. Got it? Let me skip and start from this one. So here goes the notion of random experiment. And I asked Gemini to draw this block diagram, kind of. So what we are going to do is this. First, we introduced the notion of a random experiment. And random experiment, as the terminology says, is something uncertain in the experiment. And experiment is not that kind of chemical something or physical something. Just think about your experience. Okay? And this random experiment is different from usual experiment in that it so-called has, at each trial, it has an outcome. So as you learned in high school math, tossing a coin or rolling a die is actually can be viewed as a random experiment. So here is a box inside. This is me, and you just touch the box and, hey, give me an outcome. Then what do? Here, I roll a die and shows you some number. And this number could be in the rolling a die experiment, a number in the set 1 through 6, right? So you all know this story, right? However, probably you never or rarely heard about this terminology, random experiment, and you are kind of hitting the box is called trial, that is in Korean 시행, and the output of this box is named as outcome. It can be translated as 결과 or something. So you have this kind of block diagram you've seen in signal-gen systems. Usually in signal-gen systems, you have a block and input arrow and output arrow. And this means input signal. And you have output signal. A very special system does not have this input. Of course, some random experiments, you may say that we have some input. But for the time being, just forget about the input. Just view random experiment as a box that generates some output. Whenever you hit the box and say, hey, open sesame or something, okay? Then what is an event? Translated as a 사건. The event is a little bit different. For example, when you're rolling a die, as an outcome, it can be a number from 1 to 6. However, an event may be something like this. Outcome is an even number, right? Outcome is an even number. Outcome is 6. Outcome is 7. It's different from outcome is an even number. So what does this mean? Actually, your event is a kind of subset of this one. Right? So you see the difference? Yeah. And these motivational figures actually shows the importance of set theory and related mathematical definitions, plays an important role to precisely model random experiment, and furthermore, precisely model something uncertain. Got it? So as most of the textbook does, we are going to review A intersection B, A union B type thing soon. Got it? But key is that in order to precisely describe a random experiment, we rely on theory and terminologies there. So element over set and element, inclusion, complementation, union, intersection, something like that. And so far, you all know, right? You've seen this type of progress in other courses too. And here, set is translated as chip-hop. And as you've seen, if you collect all the possible outcomes of that random experiment where you roll a die, then you may construct a set that includes all possible outcomes. This set serves as a universal set in our set operations. And this set is called the sample space of the corresponding random experiment. For example, okay? And what is an event now? Now you can interpret an event as a subset of this sample space, the universal set. For example, what is this event? The outcome is an odd number. What is this event? The outcome is 1. Got it? And interestingly, we have the empty set. And you may say then, hey, outcome is nothing. Is that important? Actually, yes. That probably confused you when you first confronted this one, when you learned the probability theory in probably middle school. But we need this. And we will see why we need to consider this kind of strange event. Okay. Anyway, so at this moment, just take an event, take it this way. An event is simply a subset of the sample space. Got it? Now, what is a probability? As emphasized in the first class meeting, we are not going to just say probability. We are going to say always probability of an event, right? So the probability of an event something, A, right? And as an engineering student or science, we studied mathematics. And we've seen something very similar in sound. Probably you've seen this notation. What is this? What is the standard meaning of this one? F is a function, right? F colon, right? F is a function. F is a function. What is this one? This is so-called domain of the function f. And what is this one? This is sometimes called domain of the function f, right? So you just say fx, but in precisely speaking, this must be read as what? F of x, right? Now, let's make one-to-one correspondence. These two matches. These two matches together. And you have what? So actually, probability of event something is closely related to f of x. You are familiar with. So from now on and throughout this course, we are going to see or understand the probability as a function. So probability, precisely speaking, probability measure is a function. Got it? So from now on, whenever you are asked, especially in this course, in quiz or exam, if the question is, what is probability? Then your answer is, it's a function. Got it? But we want to kind of refine it more by putting more adjectives. What does this mean? A set function. A set function. What does that mean? Input of the function is a set or output of the function is a set? Of course, it's not that clear. For example, in our math, if I say a real function, real valued function f, what does it mean? Output is real, right? Complex function f, output is a complex number. But here, the set function means the input is a set. Okay? So unlike most of the functions you learned so far, this probability measure as a function has a domain consisting of sets. And we are going to see something like this. By the way, what's the meaning of bracket 0, 1 bracket? It's an interval that contains all the real numbers from 0 to 1. Okay. So this is the codomain of the set function P. And you want to ask, what is this E, right? And depending on the textbook, some people love F but let me use E. This must be a set because domain of a function is a set. So this itself is a set. The problem is that, as you see here, what is the input to the function f? You select one element, one member of the domain, and put it in the parentheses, right? So f of 5, something like this. Now here, for the probability measure, you have to put what? An element of this set. And the element of this set is another set, a set. So for example, in the coin, the rolling die problem, we want to, even numbers. We want to put this set consisting of 2, 4, 6, to compute the probability of the event that the outcome is an even number. So sometimes I will just say probability of even number, but that is not precise, even though I will say that. As I told you, probability of the event that the outcome is an even number. That is the full description or correct description I want you to write down in your answer booklet when you take an exam. So do you have something little bit clearer than before? So let's understand the probability as a function. And that function accepts sets to generate a real number from 0 to 1. So that E, the set E, denoted as this capital E, includes what? Events in our case. Because events are what? Subsets of the sample space. Got it? Anyway, so I believe this is the first thing. Probably you think, oh, okay, this course sounds a little bit different from high school probability theory. Got it? Okay, so I believe you are now well prepared to understand the next sections. So we are going to review set theory terminologies very quickly. I will skip most of them. So you know what is a set, you know what is an element or a member of a set, and you know how to read it. S is in A, or S is a member or an element of A. By the way, you'd better know how to read it. Because what I have found is that very well prepared graduate students even fails in their first presentation because they do not know how to read mathematical expressions in English. Okay? They always say that, look at this, look at that, this is that. So I hear a lot of this and that. Okay? But I recommend you from now on to take more attention, pay attention to how to read mathematical expressions in English. Okay, S is a member of the set A, and this is S is not a member of the set A. And here goes an interesting function called indicator function. And in some textbook, it has an alias called characteristic function. But I really hate this one because the characteristic function, the terminology is going to be reserved for something different from this. Got it? So I will strictly call this function as an indicator function. And this function has something interesting. In the subscript, this one is always there, okay? 1, and you have some subscript. And by the way, subscript. Throughout this course, I will just say A sub something. I do not want to spend my energy and time to read all the vowels and consonants in this word. So A sub S, okay? One sub A of S, okay? What does this mean? Interestingly, this is a set. And this means the argument of this function. So actually we have, precisely speaking, we have something like this. So suppose that we are given a universal set, or we have some agreed universal set. And from that set, we choose a member and plug in here. And if that thing is a member of this set, then it will return 1. Otherwise. So it really indicates the membership of the argument to the subset put in the subscript. Got it? And this you will find a lot of interest, especially later if you want to prove so-called the inclusion-exclusion principle you learned in high school math. Probably you remember, right? You start from 2 subsets A and B, and the question is write A union B using probability of A union B in terms of probability of A and probability of B and probability of A intersection B. And then what do? You introduce 3 subsets. And still you can draw a diagram and do it. What of O and general N? And probably you know, and you did the proof by using mathematical induction. But if you use, let me give you a hint, it's a kind of spoiler, but if you use this indicator function, you can derive the general formula much, much easier. So if you are interested, just do it before I show the result in later chapters. So you must wait my derivation until we cover the expectation of a random variable. So one more spoiler is something like this. Let me see. No, I'm not going to spoil it. Okay. Let me delete. Okay. Anyway, by the way, you must distinguish this symbol, empty set, with looks similar, phi. This is the empty set. So they are different. Anyway. And also, you know, whenever you describe a set, there are 2 methods. In Korean, what is that? 원소 나열법. So that is tabular method. And 조건 제시법, that is the rule method. Okay, anyway. So far, just terminologies in English. And here goes another set of terminologies, subset. And proper subset. They are a little bit different. And terminologies like mutually exclusive, that is the same as disjoint. And also we have a class or sometimes a collection. And here was something interesting called the power set over set. Okay? And here was interesting notation. You have 2 and S. Okay. Okay. Far away. How do you read it? This one. In English. That is the problem, right? Precisely speaking, this is what? 2 raised to the power of S, right? And this is too long, so what do we do? So we skip these things and just say 2 to the S. Ready? So what is this 2 to the S? 2, by the way, what is this one? This is the base, and this is the exponent. So it seems like I'm teaching English, math English. But anyway, so we have a set in the position for the exponent. What does that mean? So here goes the distinction between definition and notation. As I told you, definition and notation are different things. This is a simple notation to define some set. Okay? And this notation is borrowed from our previous knowledge like this, 2 raised to the power of 5. And this strange notation means what? 2 to the S, named as the power set because we have here power, right? Contains all the subsets of the set S. So now let's see an example. Suppose we have the universal set having 2 elements, heads and tails. I really hate why there is the S to mean plurality. But anyway, heads and tails when you toss a coin. Then the power set 2 to the S is a set that includes all the subsets. And now you've already noticed, hey, the number of elements of the power set is what? 2 raised to the power of the number of elements of the set, named cardinality. Okay, so we may generalize for the case where cardinality of S equals N. In that case, how many? We have 2 to the N distinct subsets, which means that the power set has 2 to the N distinct members. This motivated the notation. Okay? We are not multiplying 2 S times. we don't do that. This is just a simple notation. So this kind of so-called abuse of notation will appear again and again and again and again and again and again and again throughout this course. That confuses you. Last time I've given you already. You all know what is this one? Expectation over random variable X. But most of you have no idea what is the expectation of X given Y. Here, Y is not an event. This is a random variable, which means scalar with uncertainty probabilistically modeled. And this is another random variable, means scalar with uncertainty probabilistically modeled. Most of you have no idea, even though you have taken probability and statistics. and even though you have taken high school math and already have seen the expectation. Okay. By the way, here goes some visualization tool called a Venn diagram. Precisely speaking, some students long ago approached me that, hey, professor, precisely speaking, what you say a Venn diagram is Euler diagram, and it's different. So it's kind of, again, abuse of definition. But anyway, as you already know, this is called Venn diagram, okay? And if you use this one, you can easily prove the inclusion and exclusion principle for 3 subsets of S. But what if we have 4 subsets, A1, A2, A3, A4? And I asked Gemini, and Gemini said that, hey, professor, even in the plane, 2D plane, actually, we can draw a Venn diagram with 4 subsets and precisely derive the inclusion and exclusion principle. Just examining that Venn diagram. So if you want and have interest, just do that. I will not block you to do that. But okay, let me skip. By the way, here goes very, very important thing. And if I have taught you signal gen systems, probably I would have told you this thing in the signal gen systems. So here goes the question. What is the major difference between high school math and university or college level math? Now you know there are mainly, I'm not saying that there are mainly 2 different types of infinity there. One is so-called countable infinity, and the other is uncountable infinity. In the context of the set theory, probably you already know that the set of natural numbers or integers or rational numbers are what? Countable sets. And the set of real numbers is uncountable sets. But both of them, not both, all of them has how many elements in the set? Infinity. So infinity in the above is different from infinity in the below. But in our high school, just we said infinity. However, now we have, of course, we still use this one in college level and even graduate, but we know that there are 2 different infinities. One is what? Countable infinity, and the other is uncountable infinity. And this is very important. And mathematicians say RF not or RF null to mean countable infinity, and RF1 to mean uncountable infinity. By the way, this is very, very important. For example, in signal gen systems, you learned the sampling theorem applied to a continuous time signal. So you have a time function that spans from negative infinity to positive infinity. What does that mean? A function means that you have a pair of numbers. At time t, you have some number, right? Now let me ask you the question. How many pairs do we have to describe a time function? Infinite. What kind of infinity? In this case, uncountable infinity, right? Because for every t, which is a real number, we have a value. So we have a pair of t and x of t for every t. So we have, in this case, this pair, how many? Uncountably infinite. But in sampling theorem, what does that, what do we do? We do something strange. So let me use this one. We sample here, there. So this axis means sampling instance. What does that mean? We take this value, that value, that value. And now if this sampling interval is capital T, how many pairs do you have now? You have nt comma x of nt, where n is an integer. So now you have countably infinite number of pairs. The sampling theorem, Nyquist, says what? They are the same. And this is right. I already told you countable infinity is different from uncountable infinity. So in terms of this countability and uncountability, sampling theorem is a kind of magic. You have uncountable infinite pairs, and suddenly you discard almost all of them and have countable number of pairs, and you claim that it's enough. I can reconstruct uncountably infinite pairs. Surprise, surprise, right? Anyway, you never have viewed a sampling theorem in that way, so I kind of teased you. Anyway, so far so good. And I really want to emphasize this one. We, from high school math, we did a lot of things like this. Okay, t tends to infinity, x of t in control systems, final value theorem, something. What does this mean in the engineering problem? Do we really think about infinity? And also, when I was at your age, I really hated this one. Hey, as a Big Bang believer, right, we cannot go back to infinity. Probably some 138억 년. I don't know what is in English, but anyway, 138억 년 is not negative infinity, right? Then what's the engineering meaning of plus infinity or positive infinity or negative infinity? It's so-called for sufficiently something t. Okay. In this case, just limit t to infinity or t tends to infinity means for engineers for sufficiently large t. But we don't know what is sufficiently large. 1 second is sufficiently large, or 1 billion years is sufficiently large. We have no idea. Sometimes 1 microsecond may be sufficiently large t. If we transmit, for example, in terabits per second, something like that. But anyway, as an engineer, we have to deal with that kind of thing for sufficiently large t, or for sufficiently small t, or sufficiently far, far away, long, long ago, something like that. To handle that mathematically precisely, we use limit operations. You have to remember this one. Got it? And the last one before we move on is, again, existence and uniqueness. Whenever you define something, even if it is not that meaningful, try to check existence of what you have just defined and whether what you have found existing is unique or not. That clarifies a lot of confusion. The reason is that in Korean language, we don't have such things. The and s meaning plurality. For example, I wrote some document and sent to the university, and the university paper, and the editor returned my manuscript, removing all what? I sent in this way. 학생들을 가르치고, and then they removed this 들, meaning s. And also, sometimes because I'm much better in English than most of the Koreans, then the editor deleted this one. I really wanted to, the person. What does this mean? probably at this time of LLMs, translating almost perfectly to Korean language from the English written documents or textbooks, some of you may believe that, hey, I don't need to study that hard in English. The English is not now important. Let me just use LLM to translate. That's not good, okay? Because Korean language, I dare say, is 틀림없이 이 말하면 또 뭐라고 SNS에 막 올릴 것 같은데, don't do that. I will find you who uploaded. Is an inferior language compared to most of the Western languages like English or German or French. In what sense? We don't have articles or the. We rarely use that as meaning plurality. But as you know, Japanese and Chinese is also very inferior. Even Chinese languages does not have past sentence, something like that. And all the precise meanings are inside the context. So we, Eastern Asians, have a big problem having very, our character may be very, very superior, like Hangul, right? But you all know the difference between language and character. Our character is one of the best, but our language is one of the poorest. Probably little better than Japanese. Okay, they also have serious problem in this. So pay attention to this, and suddenly you will find why I emphasize the existence uniqueness. Because if some mathematical textbook is written in English, German, or French, by just reading the definition, you can instantly notice whether that thing is unique or not. Because in that case, they put the article the. But we don't have that. So we read through the Korean version or Korean translated book to understand. Right? Anyway, if I have enough time, I will talk about this problem related with Pascal, the mathematician, but I don't have enough time. I have just around 25 minutes. Now, let me move on to section 1.3. Now, we have so-called set operations. When I was a first-year elementary school student in 1977, probably your parents, some of your parents was not born, okay? The first math course, this is the blackboard, and there was another board, and our teacher with 67 students. Can you believe that? At that time, one class had 67 students. And our teacher had a very interesting board with colored papers. And there was something like this. And it had big plus sign. And she tried to teach us so-called the addition operation. So what she did was that, hey, here you have 3 apples, and you have 1 apple, and put it together, and you shake it. Then how many apples do you have in bottom? And everybody said, 저요, 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 저요. Right? This is the operator. Ready? So it's very similar to function. And you may say that, hey, what's the difference between function and operator? Philosophers and mathematicians distinguish them, but I don't know exactly. Okay? So let me just call it operator. Now, the difference is that we are going to do set operations. So what's the difference? We have a set goes in here, another set goes in here, and we have one more set. This is 2 input, single output set operation. And interestingly, U, the union, or intersection are the most fundamental things. By the way, there is one more single input, single output set operator called complementation or complement. So as you all know, if the set A goes in, you have A complement. By the way, the difference between these two input, single output, for this complementation, we need to assume what is the universal set, right? Otherwise, how can you get the outcome? So whenever we talk about the set, probably we assume a universal set. Got it? Anyway, as you learned in logical circuits, introduction to logical circuit, interestingly, this complementation corresponding to negation, not, and intersection and union corresponding to and or, operations are the most fundamental operations. All the other operations can be derived from these three. As you know, the set difference and symmetric difference can be derived from these things, right? And probably you yourself find what they are. Anyway, so we have A intersection B, that is what? Two input, single output operation. And interesting thing is that if you switch the left input with the right input, the answer is the same. Can you believe that? I learned that when I was an elementary school student. My teacher said that, hey, is it interesting? You switch the input to this adder, you have the same result. And most of the students said, and I said, who? I still remember that, okay? It was very shocking, especially when I was a second. I really hated this one. Why they are the same, right? Something like that. But anyway, you see something very similar. And now, these things makes a lot of sense. Because when I was a high school student, I didn't know why the 수학의 정석 shows this one. So obvious, right? Why we have parentheses? Okay, to ask me to compute the union first. But actually, here, what is interesting is this one. This notation is not legitimate yet unless we prove something. Because union is what? Two input operator. So what does this mean? Without proving these are equal. And also, of course, this one, okay? So since we have commutativity and associativity, actually, we can just drop the parentheses. Got it? Anyway, associativity, De Morgan's law, you all know, right? So let me just skip it. And here goes something you've never learned in high school, but you still instantly understand. Suppose now you have a sequence or n subsets of a set, universal set. Now you want to compute the union of this one. By the way, is this notation allowed? Yes. Why? Because any rearrangement of two set operation gives you the same thing, right? That is used by Gauss to compute this one, right? He just grouped this way. Why? Why that is allowed? Because any rearrangement gives you the same answer. Same thing. So here, this one is true. And here goes the notation, okay? Union from I equals 1 to n of a sub I. Same thing here, and it's not that difficult so far. And here goes something you've not seen, but that's not that difficult. See that? This kind of upper limit is now changed to infinity. So you have so-called countable union, a union of countable subsets, and countable intersection, the union of countable subsets. Intersection of countable subsets. So far, it's okay. And even you can solve this kind of example. Suppose you have a subset A sub n, that does not include the right and leftmost points, but include all the real numbers between these two. And now you consider intersection of all A sub n's. Then what do you have? You have this one, right? Something like that. And you can find a similar example involving countable union. Here comes something interesting. Sometimes we need to extend countable union and countable intersection to uncountable union and uncountable intersections. And you see how they are denoted and how they are defined using exists and for all symbol. This is just, you can do it yourself type thing. Now, here goes something rarely taught in undergraduate probability courses, but we remember the notion of f of x is continuous at x0, or f of x is a continuous function. From our high school math or elementary calculus, right? I told you the probability or the probability measure is a function. So we want to kind of have something similar to the continuity of a function. And very, very interesting result is this one. I'm not going to prove it, because if I want to prove it, it becomes kind of major theoretic course. Interesting thing is that any probability measure is a continuous function. Which means that this holds if exists. So if you have a sequence of events in our context, or sequence of subsets that converges to another set, then you can switch the order of this function and the limit operation. That is continuity. Because you already know this one, right? What was that? Limit x to x0 of f equals limit of x0, right? So you have the same thing. And probably most of you will never take the graduate level probability and random processes, but most of you, if you stay in electrical engineering, will use this one without proof. You are going to switch the order of probability measure and limit operation. So I just want to emphasize that there is a notion of what? Convergence of a sequence of subsets. You learned convergence or non-convergence of a sequence of real numbers. But in probability theory, we for the precise derivation, we need the notion of convergence of events, convergence of a sequence of events. I'm not going to talk too much about it. If you have interest, just read it. And probably we will not see this one but anyway. And here was really a graduate level or math-oriented one. Probably you've heard about limit supremum and limit infimum of a sequence of real numbers. We have the counterpart for the sequence of events. So lim sup of what? Lim sup of what? This is the nth element, member, nth term of a sequence of events. This is the nth term of sequence of events. And this plays important role as they played important role when we handle sequence of real numbers. Anyway, I'm not going to talk much about it, as I told you, gone. But if you have interest, then try to read it. Anyway, the next Monday is a holiday, so you have enough time to read it. Okay, let me skip. And here goes 1.4, and we have around 12 minutes. Let me do my best. So here goes the notion of probability space and the axioms of probability measure. This term is also rarely spoken in high school probability course. And here goes the most important thing, most important phrase, sentence or phrase of today. So given a random experiment, right, box, and if hey, then there comes the outcome, right, with uncertainty. That is a random experiment and trial and outcome, right? This is mathematically modeled by so-called a probability space. And this space is not three-dimensional space, something like that. It's a kind of mathematical space. It's actually collection of three things. And probability space has sample space. And this is not event space, but people call event space and probability measure. And three things put together is called a triplet. Duet, if we have two, right? This is duet. So by using three things, sample space and event space and probability measure, we describe a random experiment. And three things put together is called a probability space. So given a random experiment, you must be able to find the probability space. Got it? Otherwise, you haven't yet fully described that random experiment. The problem is that this set E that contains events is very subtle thing. Most difficult questions arise from this one if you take the major theoretic probability course. However, I promised you not to talk too much about it, so let me be very, very quick. Okay? First, sample space is easy. As you already know, it contains all the possible outcomes of a random experiment as members. And here goes terminologies. And we all know, right? Rolling a single die, tossing two coins, we have sample space like this. But this event space, precisely speaking, this one, a duet, is a very strange thing. Anyway, here goes the most formal, but avoiding major theory type definition. So, given the sample space of the random experiment we are interested in, what we do is that we find a collection. This is very, very important. As I told you, pay attention to that article. we find a collection of some subsets of S. Some, not all subsets, okay? Some subsets. And these subsets, you apply any countable set operations, complementation, intersection, and union. And if the result is still in that collection, then that is now can be used as this set E. And if this holds, this E is called a sigma algebra of subsets of S. Here, again, you will see why. So consider the most simplest sigma algebra of subsets of S. Empty set and the sample space itself. Now you apply complementation, union, intersection. What do you do? What do you have? Still empty set or the sample space, right? So that E I've shown you, very trivial, is what? Is a legitimate collection called a sigma algebra of subsets of the sample space S. Now let's say something more. Suppose you have a finite sample space, like rolling a die. In that case, the sample space has 6 members. In that case, what about the power set that have all possible subsets of S? Is that a sigma algebra of subsets of S? Yes. Okay. And probably you just thought that the power set is the event space. But actually it is not. That's what I'm saying. Now, this is also a legitimate sigma algebra of subsets of the sample space S. See that? You apply any countable set operations on these 4 subsets of S. You still have one of them, right? Am I true? Yeah, am I correct? So that is also okay to form an event space. As I told you, event space is a duet, but even I myself show you, in many undergraduate textbooks, the set E is called the event space, which is a white lie. However, that's okay. 99% of the engineering professors and students, they just call E as the event space, even though, precisely speaking, it is a sigma algebra of subsets of the sample space. Why do we need this? And many of you have noticed that, hey, this is nothing but a kind of closure after operation, right? What is algebra? Basic algebra is addition, subtraction, multiplication, division. And for the real number, we have closure, right? We apply countable operations and we have real number. What about the set of rational numbers? We don't. You know that, right? 1 plus 0.4, 0.001, 0.004, and you know what I'm doing, right? Square root of 2. And that is what? We apply countable addition of rational numbers, and we eventually have what? An irrational number. So that's why we say that the set of rational numbers is not closed under countable algebraic operations. That's why we need real number set, right? Same thing here. What we want is that after some set operations, we don't want the result, the event or something out of what we are going to think about. So it's about kind of closure. And this is really cumbersome thing. So if you want to take the graduate level course or math major theory or major theoretic probability, probably you will spend a lot of time in understanding what is a sigma algebra of subsets of something. Anyway, what I want to say is this. why we need this notion? For a countable sample space, which means that the sample space is a countable set, we don't need this notion. Actually, the power set is enough. We can just choose this way for the event space and everything's okay. However, when we have uncountable set, as here something says, 2 to the s, the power set of the sample space is too large. And the major theoreticians have shown that there are some subsets in the power set. We cannot determine what is the probability or what is the measure of that subset. That's not good, right? So we kind of discard some of the subsets and have very small sized subsets of the sample space. That is a sigma algebra. And especially when we handle real numbers, we have Borel sigma field or sigma algebra. And this is very, very important. And some of you already have seen the CDF and PDF. And so let me show you. CDF over random variable x is what? Probability of x less than or equal to x, right? So we have an interval like this. Why? Because Borel have shown that so-called the Borel sigma algebra is enough for our engineering science application. And that sigma algebra is generated, it's complicated idea generated, but anyway, generated by such half intervals. Got it? So the intervals like this, from negative infinity to up to some real number x. These semi-open intervals are enough. That's why probability, cumulative probability distribution function plays very, very important role in describing the distribution of a random variable and also random vectors. Oh, okay, I have only 1 minute. Here goes the axioms. Probably you've seen these axioms in many textbooks. The difference is that some textbooks shows more than 3 axioms. But actually, these 3 axioms are the axioms, minimal axioms. Then why the other textbooks talk about more than 3? It's because they are not spending enough time to describe what is this E. Because we already assume this E, the set, E is a sigma algebra, which means that it is closed under any countable set operations. We don't need, for example, the proof like, where it is? Proof like P of A complement equals 1 minus P of A, something like that, or P of empty is 0 for this one. We don't need this one because we assume that already S comma E is the event space where E is the sigma, a sigma algebra of subsets of S. Anyway, I will assume that I have covered up to here. Oh, okay, here goes it. And there will be the first homework due probably on next Wednesday, just before, is Wednesday? Yeah, just before the Wednesday class meeting. Okay, have a nice long weekend.